Hello there. So this is video number 1 of section 2.2. We're going to do some really interesting stuff today. And so I want to motivate it with the following sentence of remembrance. So remember that, let's suppose we have 3 square matrices, A, B, and C, and they're n by n. And there's a reason I've chosen them to be square matrices. Remember we have this sort of fact which I'd mentioned, which was more of a warning at the beginning of some section, last section actually, with matrix multiplication. Just because AB times AC, nope, AB is equal to AC, right? So just because these two products are equal, this doesn't always mean that B equals C. And we saw an example of this, right? Specifically when A was whatever matrix we chose, A to B. We didn't always get this. But that makes me really unhappy because notice we always do get this with real numbers with one exception. So notice, so if, let's say I just have scalars x, y, and z, if xy is equal to xz and x is not equal to 0, right? Well, what I can do, right, is I can multiply both sides of this equation by x to the negative 1, right, which is just 1 over x. So this is 1 over x times x, and 1 over x times x z. And I get that this implies that y equals z. Right, so notice that with real numbers, right, so here x, y, and z are just real numbers, as long as x is non-zero, x has this property that there exists 1 over x such that I can multiply both sides. And specifically, this happens because, right, x inverse times x, which is equal to 1 over x times x, is equal to 1. And so what this property of real numbers, what we sometimes say in math, is that this is the multiplicative inverse of x, 1 over x, and 1 is the multiplicative identity. So just like with real numbers, if I can find some matrix such that, this matrix times A gives me the multiplicative inverse of matrices, and remember we actually introduced the multiplicative inverse, I think, last section, then we might run into a situation where this is true. So I'll erase this real number stuff. We will define a specific condition when this would be true. We'll see, I guess, sort of why that makes this true. And then we will talk a lot about these specific types of matrices. So we say that a matrix A is invertible. And it specifically has to be a square n by n matrix. A is invertible if there is a matrix and we'll denote this matrix A inverse, so just A to the negative 1. And so, again, more with maybe like the bad notation in math, this isn't take all of the entries of A to the negative 1 power. This is a very different thing. This is A inverse. And we'll see that this is a very different thing from what this initially looks like. So be really, really, really careful. This notation means A inverse. So invertible, if there is a matrix A inverse such that A times A inverse is equal to A inverse times A is equal to the identity matrix. And so notice we actually get a couple things out of this. And so we call A inverse is the inverse of A. So this matrix here is the inverse of A. A, we say, if this matrix exists, is invertible. And so this matrix doesn't always exist. We will start to see some conditions which will make this matrix exist today. Notice also one thing we didn't get, which I don't have on the board, is that remember matrices didn't always with multiplication commute, right? So just because we didn't always have AB equal to B times A either, but a matrix and its inverse will always commute if the inverse exists. So this is saying that A times A inverse, equivalent to A inverse times A, is always equal to the identity matrix. And so notice, if A inverse exists, and I have AB equal to AC, well, what I can do is I can multiply both sides of this equation by A inverse, right? And so A inverse times A is just equal to the identity. But remember, we learned that the identity matrix times any matrix, it's just the original matrix itself. And so this actually does imply that B equals C. So this is actually the condition we need to make this implication true. So if AB equals AC and A is invertible, then we get this nice property. So when do we get, right? And so you can think like the reason this property held with real numbers is because we could, in a sense, cancel out like factors on either side of the equation. And this is what gives us the ability to cancel out A in that way, is that I can multiply both sides by its multiplicative inverse. How do I determine when a matrix is invertible? Well, it's not easy. We're going to learn how to do it with 2x2 matrices today. And then, well, not today. I always say today. This lecture, we're going to learn how to do it with 2x2 matrices. And then we will learn next lecture how to do it with 3x3 matrices. Unfortunately, 2x2 matrices, we have, 2x2 matrices, we have sort of a nice way of doing it. Everything else it gets kind of annoying once you start to get higher dimensions. But that's why we have computers, I guess. So just a quick note, sometimes if A is not invertible, we'll call A singular matrix. So if A is not invertible, we sometimes say that A is singular. If A is invertible, then A is non-singular. And so just more definitions that will sometimes get used. I probably won't use these two definitions a whole lot. You might see them pop up in your book, and they do pop up occasionally in math and other areas of applications of this. So keep these two definitions in mind. Singular, and in particular, it's a little confusing, but singular means not invertible, and non-singular means invertible. So, we'll start with our first theorem of the day. This is 2x2 matrices. So this is when is a 2x2 matrix invertible. All right, so let A be a 2x2 matrix. And we're actually going to define A in the following way. A, B, C, D. And so notice here in particular, these are just arbitrary real numbers. So we're defining this to be as general as possible. If A times D minus B times C is not equal to 0, then A inverse exists, and we actually know exactly what A inverse is. it's 1 over AD times BC. And so notice, again, this is a scalar. So this is just the value 1 over this number times the matrix negative A, negative D, C, B. So if this value, AD minus BC, is non-zero, oops, sorry, I actually got that backwards. I did the negatives. So it's D, A, negative B, negative C. So I apologize. This is the inverse of A. So you swap the diagonal entries, and you multiply the off-diagonal entries, so the non-diagonal entries, by negative 1. And this will always, assuming this value is non-zero, find you the inverse of A. What's really nice is if AD minus BC is equal to 0, then A is not invertible. So this is a very, very nice case where for 2 by 2 matrices, we can quickly determine the inverse of the matrix. We'll first determine, does the inverse exist in a very quick fashion, and then calculate the inverse if it does exist. And so this value here, AD minus BC, actually has a name, which I will define now, and we will talk about a little bit more in detail in, I think, chapter 3. So if A is a 2 by 2 matrix, then AD minus BC is the determinant of A. And so we'll sometimes write DET, A is equal to AD minus BC. So we'll sometimes abbreviate the determinant with that DET notation. We won't talk about this much now. It's just sort of happenstance that we're introducing it, that it sort of pops up in determining whether or not a matrix is invertible. And so it kind of pops up now. I don't think we'll mention it much for at least the time being, but we will talk about determinants quite a bit later on. All right, so let's put this nice theorem to work and do an example. And actually, we don't really need that anymore, so. So let A be the following matrix, 3, 2, 7, 4. Calculate A inverse if possible. So what we want to do is first answer the question, if possible, and then if possible, we will calculate A inverse. So first step, we want to calculate A times D, which is 3 times 4, minus B times C, which is 2 times 7. This is equal to 12 minus 14, negative 2, which is not equal to 0. And so, if possible, the answer is yes. So, because if possible is true, again, actually at this point, for 2 by 2 matrices, A inverse is not going to be that hard to find. Remember, it's 1 over this value, so 1 over negative 2, times, well, I swap the diagonal entries. So for 3, multiply the off-diagonal entries by negative 1, And what I can now do is just factor this 1/2 through since it's a scalar. And so this gives me the matrix -2, 1, 7/2, -3/2. And this is actually equal to A inverse. And so it's actually, for 2 by 2 matrices, as easy as that. You pretty much just have to follow the formula, check steps 1 and 2, and you're good. And so just for the fun of it, I thought we could convince ourselves that this formula was actually working and calculate the product A inverse times A. All right. Well, doing our matrix multiplication dance, matching this row up with the column, I get -2 times 3 plus 7. Sure enough, that gives me 1. -2, 1 matched up with 2, 4. That's -4 plus 4. 7/2 and -3/2. So this is 21 over 2 minus 21 over 2. Very good. This would be 7 over 2 minus 4 times 3 over 2. And so sure enough, the theorem works. And this is the 2 by 2 identity matrix. And so I'll leave it as a fun exercise for you viewers at home, that you should be able to swap the order of this multiplication and still get the 2 by 2 identity matrix. So yeah, that's how you do it for 2 by 2 matrices. So I want to do one really cool example now, I think, which is going to be funny because we've almost escaped solving systems of equations, but or matrix equations if you prefer. But we actually just found a new way to solve matrix equations. And so we're going to end by solving a matrix equation. The good news here is that we won't have to do any row reducing. So we're going to use the same matrix. So let A equal 3, 2, 7, 4. And we want to solve the matrix equation AX equals B if B is equal to 0, 2. All right, so to do this, I want to first, or to do this in the way, right, we know how a way to do this, certainly. But to show you the new fancy way we have of doing it, I want to write out exactly what is going on here, right? So what we want is we want a set of values, right, for x1 and x2 that makes this equation true. And so maybe one question you had been asking, right, like how do we solve equations with real numbers? Well, we try to manipulate the equation to isolate a variable on a side by itself. The reason we hadn't been doing that is because, remember, we couldn't really move this matrix. But because this matrix has an inverse, we can actually isolate this vector x1 and x2 on a side of the equation by itself. In particular, notice if I multiply both sides of this equation by A inverse, which we found in the previous example, and so I'm allowed to do this, certainly. I'm allowed to multiply both sides of the equation by the same matrix. right? And so all I did was I took this matrix A inverse, which we had calculated in the previous example, and I multiplied it on the left on both sides of the equation. So that means that 1, 0, 0, 1 times x1, x2, right? Because this matrix times this matrix, so this is A inverse times A. This matrix times this matrix gives me the identity. Well, I can calculate this vector. So this matrix times this vector here, I get negative 2, 1, matched up with 0, 2 gives me 2. Here, 7 halves matched up with negative 3 halves gives me negative 3. But notice the identity matrix times any vector is just the vector. And so this implies that, well, I actually just solved this system of equations because, well, like using matrix inverses, right? This gives me a solution to this vector equation, and it can be fairly quickly checked that this is in fact a solution to this equation. So what inverses now do, and I will state this as a theorem and we will finish, is vectors actually give me, again, this very nice way of, inverses give me this very nice way of solving this matrix equation AX equals B. What more is that, notice, you could have given me any vector B, and because this matrix was invertible, I could have done this exact same process with any single vector B you gave me, right, and solved for x1, x2 that made this equation true. And because of the way we did it, where any solution vector has to have this property, it also gives a unique solution. So what we actually also just showed is that if A is an invertible matrix, then this always has a solution for every B, and that solution is unique. So if A is an invertible matrix, A also corresponds to a one-to-one and onto linear transformation. And so I will state now this theorem, and we can end this lecture. So theorem, if A is an invertible matrix, and n by n invertible matrix, then for every B, so for every vector in Rn, Ax equals B has a unique solution given by x equals A inverse times B. And so we can sort of quickly, I'll give you a proof of this. I say proof because it'll basically just give the general idea or the gist of why this is true, right? So if AX, well, so just sort of note, if X is equal to A inverse times B, then AX is equal to A times A inverse times B, which is equal to B, because again, A times A inverse gives me the identity matrix. And so the fact that we get this relationship means that we always have a solution, and the fact that, you know, if a solution exists, I can always just multiply both sides of the matrix by A inverse implies that, in fact, this is a unique solution. And so we'll talk about this more in the next section, but this property of being invertible ends up being really powerful because, again, always having a solution and always having a unique solution are definitely qualities we look for in matrices and in linear transformations. So I apologize for this video going a little long. I think next video we will learn how to calculate inverses for matrices of higher dimension.